Hello and welcome back to the review for the midterm for winter 23. So question number 12 says the probability distribution below is for the average hours of sleep per night for people in the US. And you can see that people had received between 4 and 10 hours of sleep, and the likelihood of receiving that number of hours of sleep is in the second column here. It says, explain what must be true in order to verify that this is a valid probability distribution. So the first thing is that the individual probabilities need to be greater than or equal to 0 or less than or equal to 1. And the second thing is that the sum of the individual probabilities need to equal 1. It says, find the mean of the probability distribution. So this is the weighted mean or expected value. And I'm going to show you how I put this together in Desmos. So I created a table with the number of hours of sleep on the X5 column and the probabilities in the Y column. And then down below, we did a total of the product of those. And our weighted mean is 6.84 hours of sleep. Now, the next question says, what is the probability that a random American sleeps between 7 to 9 hours inclusive? So inclusive means that we're including 7 and 9. And so that means we're going to take 7, 8, and 9 and add them together. So 0.3 plus 0.27 plus 0.03 is 0.6. And then it says to calculate part C, we must presume that values for hours of sleep are, and for us to be able to add them together, that is just mutually exclusive. Okay. The probability that a random American sleeps at least 6 hours a night is, so at least 6 hours a night means we're including 6. So we're going to add up everything from 6 and above. And so that number is 0.87. And what is the probability that a random American does not sleep 8 hours per night? And that would be everything but the 8 hours. And so that is 1 minus 0.27, which is 0.73. The next question is number 13. It says, in a survey of homeowners with high-speed internet, the average monthly cost of a high-speed internet plan was $64 with a standard deviation of $12. Assume the plan costs are approximately bell-shaped. So we should be able to use the empirical rule. So it says, construct an accurate normal distribution with the appropriate labels and percentages. So we're going to use the empirical rule. That says at the center should be the mean, which is $64. And then at 1 standard deviation is going to be the $64 plus 12. So 1 standard deviation would be 76. And then 2 standard deviations would be 88. And then 3 standard deviations would be 100. And this is 34%, 13.5%, 2.35%, and 0.15%. Then we're going to go in the other direction, and then the mean minus 1 standard deviation would be 52. And again, this is symmetric, so it's another 34%. And then 2 standard deviations is 13.5, 2.35, and 0.15. And so 2 standard deviations would be at 40, and 3 standard deviations would be at 28. Okay, and we always put the variable outcomes along the horizontal, always, and then the percentages on top. So it says roughly 90% of homeowners paid monthly for high-speed internet between what $2 amounts? So we're looking for the middle 95%. And so that is 34, 34, and then 13.5 and 13.5. It's 2 standard deviations. So that would be between 40 and 88. Estimate the percentage of homeowners who pay between 28 and 76 per month for high-speed internet. And so that is not including this 0.5%. So it's including the 2.35 plus 13.5 plus 34 plus 34. And so that equals 83.85%. And then lastly, it says, would it be unusual for a homeowner to spend more than $100 per month on high-speed internet? So more than $100 would be here. And actually, anything outside of 2 standard deviations is going to be considered unusual. Either direction. So anything outside of 2 standard deviations to the right or 2 standard deviations to below the mean is considered unusual. So we would say yes, because $100 is more than 2 standard deviations above the mean. Or you could also say yes, because 100 is less than 5% likelihood. It's actually less than 20% likely, or 1% likelihood, actually, because that's only 0.15%. Okay, let's look at question number 14. So 14 says about 35% of all drivers will tailgate before passing, perhaps thinking they can encourage the car in front of them to go faster. Suppose you are driving a considerable distance on a 2-lane highway during which you are passed by 12 random vehicles. You can presume that this situation satisfies all the requirements for a binomial probability experiment. So compute the mean number of vehicles out of 12 that will tailgate. So because it's a binomial, we know the mean is equal to n times p. And in this case, n is 12, and p is the likelihood that they will be tailgating, so 0.35. And so that is 4.2 vehicles. Make sure that you have units. Compute the standard deviation of this distribution. And the binomial standard deviation is the square root of n times p times q. So q is 1 minus 0.35. And so this is let's go and calculate this in decimals. And so we're doing the square root of 12 times 0.35 times 0.65. That's the Q. And so the standard deviation is 1.652. Okay. This says describe the mean and standard deviation in context. Okay, so on a binomial, we always have to address the number in our sample size, because if the sample size dictates the size of the mean and standard deviation. So out of 12 vehicles, we would expect 4.2 to tailgate before passing, give or take 1.652. Okay, D says compute the probability that at least one car will tailgate you on the trip. Okay, so that's the probability of X equal to 1. And our distribution is binomial with N at 12 and P at 0.35. So we can use decimals to go and work on these next few problems. I'm just going to go stay in decimals for a bit to finish these next few up. So this is number 14, okay? And so we have a binomial dist of 12. .35, okay. And I'm going to make sure you do your zoom fit so that you can see. I've got other things turned on, it looks like. Okay, there we go. So we're looking at the black here. And so we want to know exactly 1. So I'm just going to go and I can click on the 1 and see that that likelihood is 0.0368. Then letter E says, compute the probability that at most 5 cars will tailgate you on the trip. So at most means that I'm going to do this same one. I'm going to actually copy that and show you again. So in this one, I'm going to click on the cumulative button because I want to include everything up to 5. It says at most 5. So I'm going to leave my minimum at 0 and my maximum at 5. And you can see that the red lines here mean those are the ones I'm including, and they're adding those up. And that likelihood is 0.7873 rounded appropriately to 4 decimals, 0.7873. And then I will show you my paper here in a minute. And then the last question says, would it be unusual if all 12 of the cars tailgated? So all 12 means that I'm actually going to go back to the individual one, and I'm looking at exactly 12. So all 12. So I'm going to click on the 12, which is over here, and it's so small 0 is coming up. It's something, but it's not. It's so small that it's not showing up as 0. As the actual decimal. So we're going to say, yes, it's unusual. I'm going to show you my paper here. There's my answers for D and E. But F is going to say unusual, yes, because the probability of X equal to 12 is approximately 0, which is less than the 5%. So remember, our rule to be unusual is less than 5% probability. And that would be this case. So catch me back for the last two problems.